All right, welcome back. This is going to be 8-3. All right, this is weak acid ionization. So we have already covered equilibrium. So nothing changes here. The beauty of equilibrium is that nothing changes. So acid ionization constant, Ka, the only thing that's different is we have a little a there. So the little a stands for acid. So we're talking about weak acids. At this point, we have really only done pHs for strong acids, which is what we were talking about up here. But if you remember, hopefully you remember, or maybe you don't know, that weak acids don't break apart completely in solution. All right, so if it's a weak acid, it's not going to break apart completely in solution. And so thus we don't get complete like reaction. The reaction does not go to completion. We get only partial H pluses and so on, right? Or OHs if we're doing bases. So our reaction there for a generic reaction, they say HA. All right, HA represents, H always represents an acid. The A is our weak acid, right? So it's an HA, and there's a couple ways you can write it. I'm going to show you both. So we can just say HA breaking down into H pluses and A minuses, right? So there's that. Or we could say, like, we could show it with water, right? HA plus H2O is going to give us that hydronium ion, H3O plus and A minus. All right. So either way works because if you remember, water is not going to show up in our equation because it is a liquid. So same difference, if you will. So our formula, remember, is products over reactants, leaving out our liquids. So Ka is going to be equal to the concentration of that, let's go with the top one, H plus, times the concentration of A minus over HA. All right, it's pretty simple. Hopefully, it's fairly straightforward. Hopefully, that makes sense to you. Make that a little smaller because it's kind of fat. All right, so that works there. All right, so let's see if we can't put this into practice. It's going to hopefully be a good review for us because it is exactly like what we did before. So, what we're looking for here in this one, we're looking for the hydronium ion concentration. We have our beginning concentration and we have a Ka. So, the first thing that we need to do is write a reaction. So, we're going to take HCN. It's going to break down into H pluses and Cn minuses. All right, our initial concentration of HCN is 0.100. This is initially 0, 0, minus X plus X plus X. So we're going to get 0.100 minus X. That's just going to be X. That's going to be X, right? All right, hopefully I'm not going through that too fast. You can maybe hit pause if that's something we're struggling with. Now remember, our equilibrium constant expression is going to be products over reactants. So we're going to have H pluses. Wow, that looks like a 7. Let's try that again. Beep, beep. All right, so H pluses and then Cn minuses, right, over HA. Okay, and let's start plugging stuff in that we know now. Trying to make this a little bit bigger, but now I can't see anything. Awesome. So we got 4.9 times 10 to the negative 10th is equal to X times X over 0.10 minus X. All right, we've got that there. Remember, these X's are going to be little things, so we can cross them out because they're very small. So multiplying across to the other side, right, we're going to take 0.10 on each side, right? 0.10 on each side. And so we're going to have X squared is equal to 4.9 times 10 to the negative 11th. I hope you did that one in your head. All right, now to get there, we need to square root that. So we're going to go ahead and just hit the square root button. All right. And so our answer for our concentration of H plus X, which is also H plus, is going to be 7. Let's see if there's anything else on that. Nope, just straight 7. 7 times 10 to the negative 367. I don't feel like maybe that's right. Can we just double check that? Okay, all right, 7. How about negative 6? Let's try that, negative 6. I can't count this late at night. All right, there we go. All right, questions there on that one. Hopefully we're good. Let's roll on. Now let's take this. This one's just going to be a step further. We're just going to find pH. Once we find our H positive, we're just going to go to pH and take it one step further by taking the negative log of it. So let's see what we got there. So kind of the same diff. This time we have nitrous acid. We'll talk about the naming and such a little bit later. All right. So we've got that. We've got our little ice chart. I hope you don't need me to write down ICE because totally avoided it on the last one, right? Minus x plus x plus x. All right, down here we've got 0.20 minus x. That's just x. That's x. So over here, Ka times our H plus times our NO2 minus over HNO2. All right, now we're ready. We've got 4.6 times 10 to the negative fourth. And yes, you can absolutely skip steps if you want to. All right. So let's see what we got there. We've got x squared times 4.6 times 10 to the negative fourth. I skipped a little bit of steps, but hopefully it was not too many. We're going to have 0.000092, or you could say 9.2 times 10 to the negative fifth. And then we want to square root that. So we find our square root button, plug that baby in. Our x is going to be 9.59. All right, 9.59 times 10. Let me blow this up a little bit because my writing's getting a little rough. Let's try that again. 9.59 times 10 to the negative third. All right, and remember that's equal, labeled molarity. Labeled molarity, and that's equal to our H plus. So at this point, we can now plug it into pH equals the negative log of our hydronium ion concentration, or H plus in this case. So we now just place negative log of that, and we get 2.02. 2.02 is our pH. We kept 2 decimals, except I think we need to keep 3. If I go back and look up there, we have 3 here. 1, 2, 3. So we should have 3 in our answer. So let's fix that a little bit. How about 2.018? All right, let's try one more. This time you're going to work backwards and find Ka. So why don't you hit pause? Try that. I'm going to work it out as you hopefully roll, but hopefully you have a pause button and trying it on your own. Like I said, we're just working backwards, same kind of diff. All right. So hopefully you came up with HA breaks down into H pluses plus A minuses, right? We've got an initial of 0.100. We've got 0, 0, minus x, plus x, plus x. All right, now at this point, we can find x, right? We can work from pH, all right, of 4.25. We can work that to hydronium ion concentration by taking our hydronium ion concentration, or H plus, right? Same thing, is equal to 10 to the negative pH, right? So 10 to the negative 4.25 will give us our H plus, which is what we're looking for. So we're going to go second log, that was inverse log, second log, and we're going to go negative 4.25 there, and we should get 5.623. Let's hold a couple here. Holy biscuits. All right, let's try that again. Get back to home. All right, so our H plus is going to be 5.623 times 10 to the negative fifth. All right, and that's our molarity. So we know our H plus, which means we also know our A minus, right? That's also equal to our A minus. All right, so we've got both of those. I'm going to be lazy and just draw an arrow to show where those go. And then we're going to take 0.10 minus that, right? Which is that going to change the sig figs in it? I mean, we can pretend, but the answer is we're going to get 0.9994. So not really. All right, and then we're just going to plug it into our expression. So we're going to have 5.623 times 10 to the negative fifth, and that's going to be squared, right? Because that's our x's over 0.9994, and you would still get a very similar answer if you just left that at 0.1. So let's see what we get here when we plug this in. 5.623 times 10 to the negative fifth, and then we want to square that. All right, and then we are going to divide by 0.9994. Notice we kept a few more in there just to make sure we had plenty. So our Ka, and we need 2 decimals, 3 decimals, we need 2 because remember we keep the least. So we're going to say 3.2 times 10 to the negative ninth. And remember Ka has no label, so there we go. All right, this video is done. We'll see you next time.